Four identical masses of M are kept at the corners of a square of side A. Find the four identical masses. Find the gravitational force exerted on one of the masses by the other masses. Let us take this as x-axis and this as y-axis, and here this is origin. Now let us find the gravitational force on this only, the mass placed at origin. Let us find gravitational force on M placed at origin by other masses. So that means this mass is pulled by this mass, and this mass is pulled by this mass, and this mass is pulled by this mass. Let's say O, A, B, C. So this force will be force on A by C. And this force is force on O by B. And this force is force on O by A. Now the resultant force will be FOA plus FOB plus FOC. First let us find FOA. Force on O by A, G M into M by distance A square into unit vector along OA, GM square by A square. Unit vector along OA is along positive x-axis, therefore unit vector along positive x-axis is I. Next FOB. Force on O by B, capital G, here M, by the distance. This is a square and this is a right angle triangle. Here A means this hypotenuse will be root 2A. So root 2A whole square into unit vector along OB, GM square by 2A square ROB. So this ROB means ROB vector divided by its magnitude. Let us find this separately, where ROB is ROB divided by its magnitude. ROB, this one. This is vector sum of ROA plus RAB. ROA plus RAB. by RAB means magnitude. ROB. O to be the distance is root 2a. Root 2a. And this is equal to ROA means AI. See, the magnitude is A, and this is in the direction positive x-axis, therefore I plus RAB, this one. Its magnitude A, and this is in the positive y-axis, so unit vector is J, A, J, divided by root 2A. So ROB becomes 1 by root 2, A gets cancelled, I plus J. So let us substitute this value here and write FOB is equal to GM square by 2A square into this value 1 by root 2 I plus J. This is third equation. Substituting these three values in the first equation, we get the resultant force. Substituting FOB. Now we want FOC also. FOA this is FOB. Next we want FOC. FOC means here. So capital G M into M by distance square into R OC. GM square by A square. ROC means this OC is along positive y-axis, therefore the unit vector is J. Now substituting second, third and fourth equations in first equation, substituting 2, 3 and 4 in 1. FR is equal to FOA GM square by A square I. FOB GM square by 2 root 2 A square I plus J. FOC GM square by A square G. Now what can be taken common? GM square by A square can be taken common. Here I remains. Plus here 1 by 2 root 2 I plus J plus J. Here I plus J, here I plus J. Here 1 plus here 1 by 2 root 2. 2 root 2 plus 1. A square into I plus J. This is the answer. The answer. Two spherical balls of 1 kg and 4 kg. This is 1 kg and this is 4 kg are separated by a distance of 12 centimeters. Find the distance of a point from the 1 kg mass Find the distance of a point from the 1 kg mass. Say from 1 kg mass at a distance. Suppose you kept some mass at which the gravitational force on any mass is said there. See, find the distance of a point from the 1 kg mass. Say this is the distance. From 1 kg mass at a distance or I kept some mass, and on this mass will be pulled by this mass as well as this mass. So the point is so chosen that the resultant of the two forces becomes 0. Okay, now force on C by A, capital G, M, here 1 kg by this 12 centimeters means 0.12 meter. Now here the distance between this and this is R square. We are considering only magnitude. So Gm by R square. Now let us consider force on C by B. Capital G M into 4 kg. By the distance between these two is here to here 0.12. From this, if you subtract this will come. So this is 0.12 minus R. So if left side force is equal to right side force, then the resultant force becomes 0. On M at C will become 0 if FCA is equal to FCB. FCA is Gm by R square whole square. Cancel. Or 0.12. Let us bring this left hand side. Here r is there. Square is equal to, here 4 is there. Therefore, here you can write, taking square root on both sides, taking square root on both sides, 0.12 minus r by r is equal to 2 by 1. Cross multiplying, 2r is equal to 0.12 minus r, or 2r plus r is equal to 0.1. 3r or 0.1. r is equal to meters or 4 centimeters. This is the answer. Universal law of gravitation given by Newton is F is equal to G m1 m2 by r square. If the SI units for G is asked, how you can find using the dimensional analysis? G is equal to F r square by m1 m2. Now force is measured in newtons, distance is measured in meter, here mass is measured in kg. So Newton meter square kg power minus 2, kg into kg, kg square, so taken to the numerator, kg minus 2. This is the SI unit for G, and this G value was measured experimentally, and experimentally G value is measured by scientist Cavendish, and that value is 6.67 into 10 power minus 11 Newton meter square by kg square. There is a long answer question. State Newton's universal law of gravitation. Explain how the value of the gravitational constant G can be determined by Cavendish method. Cavendish is the name of the scientist. The first half is already considered. Now we have to experimentally determine G value using Cavendish method. Now for that, let us take a diagram. See, in this experiment, a bar is taken, and to its ends small lead spheres are attached. These are the small lead spheres, and the length of the rod is L. Its length is L. its length is L. Now this bar is suspended by, this is suspended from a support with a fine wire. This is a fine wire. This is a bar of length L. This is a bar of length L. This is fine wire. This is mirror attached to the fine wire. Now, how they do the experiment? They bring, see, these are the small lead spheres. Just beside them, large lead spheres are kept. Large lead spheres are kept. Say the mass of the small lead sphere is m, and the mass of the large lead sphere is capital M. Capital M. The distance between these two be d. Here also same. D. So when you keep large lead spheres just beside the small lead spheres, what happens? This sphere attracts this sphere. Large sphere attracts small sphere. So immediately this bar gets deflected. How? Whether in clockwise direction or anti-clockwise direction? Anti-clockwise direction. When it is deflected horizontally, it is deflected in the horizontal plane, anti-clockwise, the fine wire gets twisted. When the fine wire gets twisted, immediately it wants to get untwisted. Further, just like simple pendulum. See, you take a simple pendulum, you move aside through some angle and leave it. Immediately restoring force brings back the bob to its original position. So just like that, when the large spheres attract the small spheres, the brass is deflected horizontally in the clockwise anti-clockwise direction, and when it gets deflected horizontally, the fine wire gets twisted. When the fine wire gets twisted, it immediately wants to untwist itself by applying restoring torque. See, when you placed the large spheres, the bar was deflected by some angle, and who is responsible for the Who is responsible for that? Deflecting torque. These two spheres produced deflecting torque in the bar, and this fine wire produced restoring torque to untwist itself. So simultaneously two torques are working. Because of this deflecting torque and because of restoring torque, because of the fine wire restoring torque. So under equilibrium, under the action of deflecting torque and restoring torque, an equilibrium position is reached. So our bar gets deflected by some angle theta, and after getting that angle theta, it gets balanced, it reaches equilibrium position. So under equilibrium position, the deflecting torque and the restoring torque both become equal in magnitude and opposite in direction. Now let us go see why this mirror is attached to this fine wire. See, when you place large lead spheres beside small lead spheres, see, because of force of attraction, see, this large sphere attracts this upward, this large sphere attracts this in this direction. So these two forces, these two gravitational forces are parallel to each other and working in opposite directions. Therefore, we call this as couple. So under the action of the two anti-parallel forces, this bar gets deflected. So, and the restoring torque inside fine wire tries to stop the deflecting bar. So under the action of deflecting torque and restoring torque, an equilibrium is achieved at an angle theta, and that angle theta must be measured. To measure the angle, this mirror is used. See how means? Here opposite to the mirror a lamp is kept. So before placing the lead spheres, the lamp light comes and falls on the mirror and gets reflected and falls on a semicircular scale. There the reading is taken. Afterwards the large lead spheres are kept. Now this gets deflected. So when it reaches equilibrium position, then so we have to measure the angle by how much angle it was deflected. So here what happens, the mirror gets deflected by some angle. So the lamp will be there only. Lamp light falls on the mirror again and gets deflected, but this time the reflected light will fall somewhere because this is deflected. By using lamp and mirror arrangement, we find the deflection. Look at this diagram here, how the deflection is measured. So from a lamp, light falls on the mirror and the reflected light falls on a semicircular scale. See the scale measuring the angle. Now it is adjusted that it falls on 0. Now when you place large spheres, because of force of attraction, the bar gets deflected. Now the bar is deflected. When the bar is deflected, this mirror also gets deflected, and this time the light falls on this side. Now here the reading is taken. In that way, the deflection is measured. The deflection is measured. See now, this large sphere attacks the small sphere. The gravitational force here is in this direction. This attracts this. The gravitational force is in this direction. So here, the gravitational force is capital G, capital M, small m by distance d square, and here capital G, capital M, small m by distance d square. So two forces are equal and parallel, but in opposite direction. So this gives us a couple. These two forces are called a couple. So couple is equal to, now let us calculate the couple, or gravitation or torque produced by the gravitational forces. The formula for couple is one of the two forces into perpendicular distance between them. See, when there is a tap, you know very well, tap will be like this. Here you apply pulling force, here you apply pushing force, so that this rotates. Just like that, on this bar, here pulling force, here pushing force are applied. Therefore this rotates, and that is called couple or gravitational torque. So one of the two forces means both two forces will be same. So we take one of them, G capital M small m by d square, into perpendicular distance between them. Between these two forces, what is the perpendicular distance? L, that is length of the rod. This is couple. Or you can write this as gravitational torque. So the gravitational torque is so this can be taken as gravitational torque or deflecting torque. Deflecting torque. Now when the bar is deflected, the fine wire is twisted, and immediately that wire applies restoring force to untwist itself. So now let us now we should calculate restoring torque. So when the wire is manufactured, so the manufacturer mentions a value on that. What value he mentions? How much restoring torque is produced inside the wire for a unit angle of twist that is mentioned. Suppose for unit angle of twist, restoring torque developed in the fine wire be tau. So now suppose the wire is twisted by theta angle. For theta angle of twist, how much restoring force is produced? Theta by 1 into tau, that is tau theta. And this is the restoring torque. Restoring torque. Under equilibrium, gravitational torque is equal to restoring torque. See here, the gravitational torque is deflecting the bar anti-clockwise. The restoring torque will be clockwise. Gravitational torque is given here. Restoring torque is tau theta. Capital G is equal to tau theta into d square by capital M small m into L. Substituting the values, we determine the G value. Substituting the values, we find capital G, and the capital G was measured as 6.67 into 10 power minus 11 Newton meter square by kg square. There is a short answer question. Derive the relation between G. The small g means acceleration due to gravity at the surface of a planet and gravitational constant. Let us take a planet. This is a planet. This is a planet. Its mass is capital M and its radius is R. And on the surface of a planet, a small mass is kept. Now, by Newton's second law, we write F is equal to mg. See here, you must have expected F is equal to ma, but here this mass is attracted by this planet. So gravitational force on this mass here gravitational force on M by capital M. Gravitational force on small m by capital M. That is F is equal to mg. Now, by universal law of gravitation, universal law of gravitation, the gravitational force is capital G capital M small m by the distance between this and this, capital R, because this is negligible from here to here, R square. This is second equation. Gravitational pull on this is mentioned in two ways. One way using Newton's second law, another way using Newton's universal law of gravitation. So, but both represent the same force. LHS are equal, therefore RHS must be equal. So this is the relation between small g and capital G. How does G value changes with height from the surface of Earth? Suppose this is Earth. Suppose this is our Earth. This is our Earth. On surface of Earth, let the acceleration due to gravity is g. At some height, the acceleration due to gravity is gh. Let me write here. Let be g on surface of Earth and gh at some height h. Now let us draw a diagram. Say first, this is Earth, and an object is on the surface of Earth, center of Earth. This is radius of Earth. Now on surface of Earth, the gravitational force on the object by Earth according to Newton's second law is mg, and suppose its mass is capital M, and according to Newton's universal law, the gravitational force between these two is R square. Or Now, at a height h from surface of Earth, that is here, this is the Earth and the object is here. Here to here radius, its mass is m, and this is h. This is h. At a height h from, see, at a height h, see, gravitational force according to Newton's second law is mg of h, because at some height h the the acceleration due to gravity is g of h, and according to universal law of gravitation, here the distance between object and earth is here to here or here to here h, so r plus h whole square. So here now we can do one thing. R plus h can be written as r plus h r by r, multiplying and dividing by r. Now you can take r common, 1 plus h by r. So here in place of r plus h, let us substitute this. Square. Now this is equal to gm by r square into this, take into the numerator, minus 2. Now you know already in your lower classes about binomial expansion, 1 plus x power minus n is equal to 1 minus nx plus n into n minus 1 by 2 x square plus so on, like that. We get a series of terms. But when x is, when here, when h is far less than capital R. See, Earth radius is very large. Compared to this, this height is very small. If height is very small compared to Earth radius, then in its expansion, just 2 terms enough, because third and higher order terms become negligible. So here then 1 plus h by r minus 2 becomes 1 minus nx 2 into h by r. So substituting here, or this is the second equation. Now second equation divided by first equation. G of h divided by here g on left hand side, on right hand side here on right hand side so that we get one minus 2h by r, or take this g that side, g into 1 minus 2h by r. In this way, we got an expression for variation of g value with height. Now, as height increases, the deduction part increases, therefore g value decreases. As you go higher and higher, because of this minus term, gh value decreases. This equation suggests that g value decreases with height. How g value changes with depth from surface of earth? To find expression for this, we make two suppositions. We suppose that earth is a perfect sphere. Actually, it is not a sphere, it is an ellipsoid, but we suppose that it is a perfect sphere. And second one, its density is uniform. Actually, its density is not uniform, because inside the earth somewhere coal or rocks will be there, where the density will be more, where just soil is there, the density will be less. Like that, the density changes from place to place inside the earth, but we assume that its density is uniform everywhere. First we will consider on surface of earth. On surface of earth, this is our earth and this is the object. This is earth its mass is capital M, its center, this is the radius, its mass is small m. Now let us calculate the density of the earth. Density, the formula for density is mass by volume. So here density of earth. So here mass of earth divided by volume of earth. Rho is equal to mass of earth is capital M, volume of earth. You are assuming the earth as a perfect sphere, then its volume becomes 4 by 3 pi r cube. So from this, capital M equal to 4 by 3 pi rho r cube. 4 by 3 pi r cube. Okay. Now on surface of earth, gravitational force on M using Newton's second law, mg, using universal law of gravitation, small m gets cancelled. Now G is equal to capital G by R square. Here the capital M value is 4 by 3 pi rho r cube. That is equal to 4 by 3 pi rho, here G value and here R value. Say this is equation 1. You got expression for G value on surface of earth in terms of density. Okay, now let us go deep inside earth. This is center of earth. So you dug the earth. The object is now here. Its mass is small m. Its mass is capital M. Now it is depth up to here. Up to here. Now it is at a depth of d. From surface of earth, the object is at a depth of d. Now this mass is attracted by the earth part which is under it. So earth part under it is this much. So this earth part only attracts this mass. This part doesn't attract. Only earth under the mass will be attracting that. So now its mass is say m dash. Its mass is m dash. Say its radius is r dash. Its radius is r dash. Now again let us find density. Now we are at depth d from surface of earth. So density is equal to mass by volume. But we assumed that its density is uniform, so density doesn't change, same value. But mass on earth mass, here density of earth is equal to mass of earth by mass of earth under m, volume of earth under small m. Okay, mass of earth under m is, this is m dash, and volume of this is 4 by 3 pi r dash cube. So from this you get m dash is equal to 4 by 3 pi rho r dash cube. Now at depth d, gravitational force on m according to Newton's second law, m gd, and according to universal law of gravitation, capital G, its mass is m dash, its mass is m, the distance between these two is r dash square, m and m gets cancelled, and g, m dash value here 4 by 3 pi rho r dash cube 1 by r dash square. We get 4 by 3 pi rho g 4 by 3 pi rho g r dash Now from here to here it is r, before ditching the surface of earth was here, and sent from here to center of earth it was taken as r. Now from this r, if you subtract this depth d value, you get r dash. So r dash is nothing but r minus d. Let me write here only 4 by 3 pi rho g r minus d, since r dash is equal to r minus d. This is equation 2. Second equation divided by first equation gives the first equation so g of d by g is equal to r by r1 minus d by r. Or taking this g to right hand side, now looking at the expression, we can say as depth increases, here because of minus sign, as d value increases, gd value also decreases. So this equation suggests that g value decreases with depth.